Hello everyone. Today we're going to be diving deep into AWS VPC and networking services. Let's start with the foundation of AWS networking, the virtual private cloud, also known as VPC. Okay, so Amazon VPC enables us to launch AWS resources into a virtual network that you've defined. This virtual network closely resembles a traditional network that you'd operate in your own data center, but with the benefits of using the scalable infrastructure of AWS. Amazon VPC is the networking layer for Amazon EC2, so you can kind of think about it as your own private, isolated section within the AWS cloud that's dedicated just to your account. You have complete control over your VPC, and you can configure it by modifying its IP address range, creating subnets, configuring route tables, network gateways, and security settings too. It's flexible, secure, and fully customizable to meet your specific needs. Okay, so let's talk about subnets. A subnet is simply a range of IP addresses within your VPC. You can launch AWS resources into a specific subnet, which gives you organization control over your network. Here's how you can use subnets effectively. Use a public subnet for resources that must be connected to the internet, like web servers, load balancers. Next, use a private subnet for resources that wouldn't be connected to the internet, something like a database or an application server that is only used for internal communication. To protect the AWS resources in each subnet, you can induce multiple layers of security. This includes security groups, which can act as a firewall at the instance level, and network access control lists, also called NACLs, which acts as firewalls at the subnet level. This layered approach is called defense in depth, and it's a best practice for cloud security. Okay, so when you create an AWS account, it comes with a default VPC that has the default subnet in each availability zone. This makes getting started very easy. A default VPC has the benefits of advanced feature protections provided by EC2 directly to VPC and is ready for you to use immediately. If you have a default VPC and don't specify a subnet when you launch an instance, the instance is automatically launched into your default VPC. You can launch instances into your default VPC without needing to know anything about VPC or networking. However, you can also create your own VPC and configure it as you need. This is known as a non-default VPC, and it gives you complete control over your network design. By default, a default subnet is a public subnet, meaning instances both receive and both have access to public IPv4 addresses and private IPv4 addresses too. This allows immediate internet connectivity while maintaining internal communication capabilities as well. Okay, so now we're going to go a little bit into default VPC components. When AWS creates a default VPC, it automatically sets up several components. Let me walk you through what parts get configured. First, it creates a VPC with a size of 65,536 private IPv4 addresses, plenty of room for most applications. Second, it creates just about 4,000 addresses per subnet, distributed across different physical locations for high availability. And third, it creates an internet gateway and connects it to your default VPC. This is your connection point to the public internet. Fourth, it creates a main route table for your default VPC with a rule that sends all IPv4 traffic destined for the internet to your internet gateway. This enables outbound internet connectivity. Fifth, it creates a default securities group and associates it with your default VPC. Security groups control inbound and outbound traffic at the instance level. Sixth, it creates a default network access control list, also known as the ACL, and associates it with your default VPC. NACLs provide an additional layer of security at the subnet level. Finally, it associates the default DHCP options set for your AWS account with your default VPC. DHCP handles automatic IP address assignments and other network configurations. Next, we're going to look at security in VPC. This operates at three main layers: security groups, network ACLs, and flow logs. Let's look at how these work together. At the top, we have our VPC connected to both our internet gateway for public traffic and a virtual private gateway for private connections. Traffic flows through a router to route tables, which then direct traffic to the appropriate subnets. Each subnet has a network ACL that filters traffic in and out. Within these subnets, individual instances are protected by security groups. This multi-layered approach ensures comprehensive protection. Flow logs capture information about IP traffic going to and going from network interfaces in your VPC. This helps with monitoring, troubleshooting, and security analysis, and you can exactly see what is happening in your network at any given time. Okay, so now let's understand the key differences between security groups and network ACLs. Both are essentially security tools, but they both work a little bit differently. Security groups operate at the instance level as the first layer of defense. They support allow rules only. You specify what traffic is permitted. Security groups are stateful, which pretty much just means return traffic is automatically allowed regardless of any rules. AWS evaluates all rules before deciding whether to allow traffic. And finally, a security group applies to an instance only if someone explicitly specifies the security group once they are launching that instance. Next, network ACLs. They operate at the subnet level, and it acts as the second layer of defense. They support both rules allow and deny, giving you a more granular control. Network ACLs are stateless, meaning return traffic must explicitly be allowed by the rules. Nothing is automatic. AWS processes rules in number order when deciding whether to allow traffic or not. Network ACLs automatically apply to all instances in the subnet they are associated with. Think of security groups as a bodyguard assigned to specific people, while a network ACL is a security checkpoint that everybody must pass through once they're leaving or entering the building. Okay, so now we're going to take a look at elastic network interfaces. Each instance in your VPC has a default network interface called the primary network interface, which is assigned a private IPv4 address from your subnet's IP range. Here's what's important. You cannot detach a primary network interface from an instance. However, you can create and attach additional network interfaces to any instance in your VPC. This flexibility is quite powerful. You can create a network interface, attach it to an instance, detach it from an instance, and then attach it to another. When you move a network interface from one instance to another, the network interface's attributes follow it, including its IP addresses, security group associations, and its MAC address. Okay, so now we're going to take a look at routing tables. A route table contains a set of rules called routes. These determine where network traffic is directed. Think of it as a GPS for a network traffic. Your VPC has an implicit router that is always there. Your VPC automatically comes with a main route table that you can modify to suit your needs. You can create additional custom route tables for your VPC to handle special routing scenarios. Each subnet in your VPC must be associated with a route table. This table controls the routing for that subnet. A subnet can only be associated with one route table at a time, but you can associate multiple subnets with the same route table. So this allows you to apply the same routing rules to multiple subnets. And if you don't explicitly associate a subnet with a particular route table, the subnet is implicitly associated with the main route table. You cannot delete the main route table, but you can replace it with a custom one that you've created. Each route table contains a local route for communication within the VPC over IPv4. This local route allows all resources within your VPC to communicate with each other automatically. Next, we're going to take a look at internet gateways. And it's pretty much just a horizontally scaled, redundant, and highly available VPC component that allows communication between instances in your VPC and the internet. So this means it's very powerful. It's built for reliability and performance, and it would not create any bottlenecks. It poses no availability risks or bandwidth constraints on your network traffic, so you don't have to worry about it failing or slowing down your applications. An internet gateway supports both IPv6 and IPv4 traffic, making it future-proof for modern network needs. To enable internet access for instances in a VPC subnet, you must complete several steps. First, attach an internet gateway to your VPC. This creates the connection point. Second, ensure that your subnet's route points to the internet gateway for internet-bound traffic. Third, ensure that your instances in your subnet have a globally unique IP address. This could be a public IPv4 address, an elastic IP address, or simply an IPv6 address. Finally, ensure your network access control lists and security group rules allow the relevant traffic to flow to and fro from your instance. Security must permit the connections that you need. Next, let's discuss NAT, also known as Network Address Translation. You can use the NAT device to enable instances in a private subnet to connect to the internet or other AWS services, while preventing the internet from initiating connections with those instances. This is a one-way door for security. So what a NAT device does is it forwards traffic from an instance in the private subnet to the internet or other AWS services, and then it sends the response back to the instances. So it pretty much just acts as an intermediary. AWS offers two types of NAT devices: NAT gateways and NAT instances. AWS recommends NAT gateways because they provide better availability and bandwidth over NAT instances. A NAT gateway service is also a managed service that doesn't require your administration efforts. AWS handles all the infrastructure for you. A NAT instance is simply an EC2 instance launched from a NAT AMI. You manage it yourself, which gives you more control but requires more operational overhead. Next, we have DHCP option sets. So, DHCP stands for Dynamic Host Configuration Protocol, and the DHCP option set provides a standard for passing configuration information to hosts on a TCP or an IP network. This includes settings like domain names, domain name servers, NTP servers, the fundamental networking information computers need. DHCP option sets are associated with your AWS account, so you can use them across all your virtual private cloud. This means you configure them once and reuse them. After you create a set of DHCP options, you cannot modify them. If you want your VPC to use a different set of options, you must create a new set and associate them with your VPC. This immutability, which means it cannot be changed, pretty much just ensures consistency. You can also set up your VPC to use no DHCP options at all if you prefer a more manual configuration. You can have multiple sets of DHCP options, but you can only associate one set of DHCP with a VPC at a time. This prevents conflicting configurations. After you associate a new set of DHCP options with a VPC, any existing instances and all new instances automatically use these options within a few hours. The gradual rollout prevents disruption. Next, we have a very important concept: VPC peering. VPC peering connection is a networking connection between two VPCs that enable you to route traffic between them privately. This is like a building with a private bridge that connects both. Instances in either VPC can communicate with each other as if they are within the same network. There is no routing through the public internet, and everything stays on the backbone of AWS's network. You can create a VPC peering connection with your VPC, with a VPC in another AWS account, or with a VPC in another AWS region. This flexibility supports complex organizational structure and disaster recovery scenarios. There's one critical requirement though. There should not be any overlapping of IP addresses as a prerequisite for setting up VPC peering. If two VPCs uses the same IP address ranges, they cannot be paired because routing would be ambiguous. Next, we have VPC endpoints. A VPC endpoint enables you to privately connect your VPC to connected AWS services and VPC endpoint services powered by a private link without requiring, pretty much just means it doesn't require the public internet gateways. This keeps your traffic on a private AWS network. Instances in your VPC do not require public IP addresses to communicate with resources in the service. Your private instances can access AWS securely. Traffic between your VPC and other services does not leave the Amazon network. This improves security and reduces latency. Endpoints are securely scaled, redundant, and highly available VPC components. This means they are built for reliability without imposing availability risks or bandwidth constraints on your network traffic. There are two types of VPC endpoints based on the supported target services. First, interface endpoints interfaces. An elastic network interface with a private IP address that serves as an entry point for traffic destined to a support service. Think of this as a virtual network card dedicated to accessing a specific AWS service. Second, gateway endpoint services. A gateway that is a target for a specific route in your route table, used for traffic destined to a support AWS service. This is typically used for S3 and DynamoDB access. Okay, so now we're going to move on to content delivery, also known as CDNs or a content delivery network. So these can be used in every use case where web services or media files are provided to end users, and those end users are spread across different geographic regions. Amazon CloudFront is a web service that speeds up distribution of your static and dynamic web content, including HTML files, CSS files, and JavaScript files, just to name a few. And it brings this to users all over the world. CloudFront delivers your content through a worldwide network of data centers called edge locations. When a user requests content that you're serving with CloudFront, DNS routes the request to the edge location that can best serve it, typically the nearest CloudFront edge location in terms of latency. This geographical distribution dramatically improves load times for users far from your origin servers. Now we're going to look at a few benefits of CDNs. CloudFront provides several key benefits. First, better customer service and a better customer experience due to faster page loading times. Content is delivered from the nearest edge location, reducing latency significantly. Second, reduced load on origin servers. CloudFront caches content at edge locations so your origin server handles fewer requests. This reduces infrastructure costs and improves scalability. Third, CloudFront is reliable and highly available even when the origin server is down. Once content is cached at edge locations, it remains available to users even if your origin server experiences issues. Finally, protection from DDoS accounts. CloudFront's distributed architecture and integration with AWS Shield provides protection against DDoS attacks by absorbing traffic at edge locations rather than overwhelming your origin infrastructure and your origin server. So, now we're going to talk about configuring CloudFront. So setting up CloudFront is pretty straightforward. So first you want to specify your origin servers, like an Amazon S3 buckets or your own HTTP server, from which CloudFront gets your files. So this will be the source of your content. Next, you upload your files to your origin servers. Your files, also known as objects, typically include web pages, images, and media files. So this is your actual content. Next, you create a CloudFront distribution which tells CloudFront which origin servers to get your files from. This registers your content with CloudFront's network. The next step would be CloudFront assigns a domain name to your new distribution that you can see in the CloudFront console. This is the URL that your user will use to access. And finally, CloudFront sends your distribution's configuration, but on your actual content to all of its edge locations. These are collections of servers in geographically dispersed data centers where CloudFront caches copies of your objects. The edge location then now know where to retrieve your content when users request it. So next, here's how CloudFront actually delivers its content to the users. So first, a user accesses your website and requests one or more objects, maybe an image file or a HTML page. Step 2. DNS routes the request to a CloudFront edge location that can best serve the request. This is typically the nearest CloudFront edge location in terms of latency, the location that will provide the fastest response. Next, if the files are already there and they cache at the edge location, CloudFront returns them to users immediately. This is the fastest scenario. If they are not in the cache, CloudFront does the following. First, CloudFront compares the request with the specifications in your distribution and forwards the request for the files to the applicable origin server. Then, the origin servers send the files back to the CloudFront edge location. Third, as soon as the first bytes arrive to your origin, CloudFront begins to forward the files to the user progressively. Finally, CloudFront also adds the files to the cache in that edge location for further requests. See, this caching mechanism ensures that the subsequent requests for the same content are served much faster. So now we're going to take a look at Route 53. Route 53 is AWS's highly available and scalable domain name system. Let me explain how it organizes DNS records. A hosted zone is a container for records, and records contain information about how you want to route traffic for a specific domain. Think of a hosted zone as a database for your domain routing rules. There are two types of hosted zones supported by Route 53. Public hosted zones contain records that specify how you want to route traffic on the internet. These handle queries from users anywhere on the public internet. Private hosted zones contain records that specify how you want to route traffic in an Amazon VPC. These are used for internal DNS resolutions within your AWS infrastructure, keeping your internal host names private. Now, let's discuss AWS Direct Connect, which provides a complete different way to connect to AWS. AWS Direct Connect makes it very easy to establish a dedicated network connection from your premises to AWS. Instead of using the public internet, you get a private, dedicated line. AWS Direct Connect links your internal network to an AWS Direct Connect location over a standard 1 as up as 10 gigabit Ethernet fiber optic cable. This provides so much more consistent network performance rather than internet-based connections. Okay, let's take a look at AWS Direct Connect architecture. This dedicated connection can be partitioned into multiple virtual interfaces. This means you can use the same connection to access both public AWS services and private resources in your VPC. A public virtual interface enables access to public-facing services such as S3. A private virtual interface enables access to your VPC resources like EC2 instances and private subnets. The diagram shows how Direct Connect integrates with your own AWS account and its environments, connecting through VLANs to your VPC's private gateway, while also providing access to services like S3 and Glacier through public virtual interfaces. So, in conclusion, we covered the complete AWS networking stack, from VPCs and subnets that form your private network foundation, through security layers, security groups, and ACLs, to connectivity options like internet gateways, NAT devices, VPC peering, VPC endpoints. We've also explored content delivery within CloudFront, DNS management with Route 53, and dedicated connectivity with AWS Direct Connect. These components work together to create secure, scalable, and highly available network architectures in AWS. By understanding how each piece fits together, you can design networks that meet your specific requirements for performance, security, and reliability. Thank you for your attention, and I hope you enjoyed the video and found it very useful.